Okay, so we're about to start chapter 17, which seems like it's way out of order, but really follows right after chapter 9. And the topic here is second order differential equations. First, a quick comment that I just feel is necessary to make. The acoustics are a little funny, I understand that. That's because I'm sitting in the breakfast nook at my grandmother's house overlooking the shores of Lake Michigan in Kenosha, Wisconsin, which is the same little breakfast nook in which I sat when I was studying for my PhD qualifying exam years ago. So it's kind of, I don't know, I think it's kind of cool. It's nostalgic. I'm not a really nostalgic guy usually, but this has struck me as being somewhat nostalgic. All right, so I think what we'll do is just jump right in to take a look at an example, and we'll talk about some of the difference here. So 17.1, let's switch over to the black pen here, is second order linear homogeneous, holy cow, Diffie-Qs. All right, now that sounds like a mouthful. I'm going to write down an example. Now my notation is going to change from Leibniz notation to Newton's notation. So I'm going to write this as y double prime minus y prime minus 6y equals 0. All right, so what makes this, first of all, second order? This part right here, let's do this in orange because that makes it a little harder. The fact that it's second order like that, second derivative means it's second order. But the nice thing is it's linear. Now what makes it linear? In that our coefficients here in front of the derivatives of y, the second derivative, the first derivative, and the 0th derivative of y, so the coefficients do not contain a y. All right, so, and for all that matter, these don't even contain an x. But they don't contain a y, that's the important thing. And homogeneous is even nicer, that this thing is homogeneous, which means that all the y's equals 0. Okay, all the derivatives or the multiples of derivatives add up to be 0. All right, so recall the first order ones, we were able to just get everything, one derivative on the left, something else on the right, and we could just integrate. This is a little trickier, so we need to come up with a, we're going to take a guess at a solution, all right? So, and whenever you take a Diffie-Hughes class, I'm like, what? Oh, everybody always says we're going to take a guess at a solution. And I think the reason they say that is because it was someone so brilliant who came up with this the first time that we can't possibly, trace their thought process. So we just have to call it a guess. It makes us feel good about ourselves. So what might work? Well, we know that all the derivatives or all the multiples of the derivatives add up to 0. So how could that be? So I've got this thing plus some function of this thing plus some function of this thing. The original function and its derivative and its second derivative all equals 0. Well, the only way I can get a function and its derivative to cancel out, like if there was a polynomial x squared, well, this doesn't have an x squared in any. If this was x squared, this no longer has an x squared, so I can't get this x squared to go away. What might work? How about y equals e to the Rx. So then y prime equals what? The derivative of this thing, Re to the Rx, and y double prime equals, one more time, bring the other r out front, r squared e to the Rx. So now it's possible, it's feasible that I could add up these things and all my e to the Rx's might cancel out. So let's sub into the original equation. So what do we have here? We've got the first derivative, or the second derivative, so it's r squared e to the Rx. Sounds like a car, e to the Rx. Minus the first derivative, which is just r e to the Rx. And finally minus 6 times the original function, which is just e to the Rx. And those things have to add up to equal 0, right? Well, so, you know, how do we got to figure out what R is. So what, you know, what do we do here? Well, notice that I have an e to the Rx here. I have an e to the Rx here. I've got an e to the Rx here, and it all equals 0. And the fact that I'm using the red pen might lead you to say that all cancels out. So that's pretty nice. So that leaves us with this really kind of an easy looking equation that r squared minus r minus 6 equals 0. Huh. Well, we know how to deal with these. So we could factor this thing. Equals 0, and let's see, 6 minus 3 plus 2, how about that? Minus 3r plus 2, leading me to believe that, let's see, r could equal 3, positive 3, or r could equal negative 2. So there's two different versions of r that would make this differential equation work. Now it turns out this pretty much always happens, and this becomes a pretty special little thing here. And I'm going to get this green dotted box because it's so special. This little thing that we solved here is called the characteristic equation. That guy there is a characteristic equation. And that really tells us all sorts of stuff about our differential equation. So let's take a look at this. We should say that. So r equals. I'll rewrite this. R equals 3 or r equals 2. So both. Let's see, e to the Rx, so, no wait, r equals negative 2 here, right? Negative 2. So e to the 3x should work, and e to the negative 2x. Right? Should work, should work. Let's make a note there that it should work. Both those should work. So let's check. All right, e to the 3x. The second derivative of that, oh, here's our original equation. The second derivative is 9e to the 3x. So 9e to the 3x minus the first derivative, so that's minus 3e to the 3x, minus 6 times the original function, which is just 6e to the 3x equals 0. 9 minus 3 minus 6. Sure enough, that one works. All right. So let's check the other one. Negative 2, you square that, it's a positive 4, right? So That's 4e to the negative 2x. First derivative, we're subtracting, let's see, we're subtracting the first derivative, so that's actually adding plus 2e to the negative 2x. Let's see, then minus 6 times the original function, right, minus 6e to the negative 2x equals 0. Wow, that's pretty cool. So what did we do here? Let's review our process, right? Max did a good job of demonstrating a cookbook kind of thing. What do? We guess the solution that's going to work. E to the Rx pretty much always will work. We sub it in, and then we cancel out all these e's, and we get this characteristic equation that only leaves r. Well, we solve our characteristic equation, and then we plug those two values of r in to the original, and we check both solutions, and they both still work. It's like magic, except it's not. So what about, let's see, 13, is this the right page? Yeah, this is the right page. What if I tried, I don't know, something like 13e to the 3x? All right, you know, what a random thing to try. Well, if I did that, let's see, y would equal 13e to the 3x. Y prime equals 13 times 3 is 39. E to 3x, and then y double prime equals, what is that, 117. 13 times 9. E to 3x. If I put all these in together, so it's the first derivative, or the second derivative, which is 117 e to the 3x, minus, over here is the first derivative, which is 39 e to the 3x, minus 6 times 13, which is 78. 78 e to the 3x equals, what does that equal? 117 minus 0. That equals 0. That checks out too. So really I'll talk about this later, but any scale, right, any multiple of a function that works will work for a homogeneous differential equation. All right, so speaking of that, I'm going to take a little sidebar here and do a little bit of terminology. A terminology sidebar. Okay, so I'm going to talk about this thing called a differential operator. And I'm going to just call it L, because this is going to save a lot of ink later on. In the current example, in the last example, L of y, so remember some function is y. When we take L of y, it really means d dx squared, d squared dx squared of y, so basically the second derivative, minus d dx of y, up here, minus 6 times y. All right, so the second derivative minus the first derivative minus 6 times the original function. All right, that's L. So then our equation becomes much easier to write. L of y equals 0. All right, so this particular differential operator, the characteristic equation of which is, of course, r squared minus r minus 6, right? All right, so let's look at some properties of a differential operator. Okay, the one is, does L of 5y equal 5 times L of y, right? That's a question. And if we said y equals, let's say, e to the 3x was one of the solutions we came up with. L of 5y equals, so that would be 5 e to the 3x double prime minus 5 e to the 3x prime minus 6 times 5 e to the 3x. And when we're all done here, this equals, because the 9 comes down there, that becomes 45 e to the 3x minus, let's see, that's 15 e to the 3x minus 30 e to the 3x. All right. Whereas if we did it the other way, if we said 5 times L of y equals, well, it's 5 times the second derivative, which is 9e to the 3x, minus 5 times the first derivative, which is 3e to the 3x, minus 6 times oh, no, I'm doing this too fast, minus 5 times 6 times the original function. And we discover that equals, sure enough, 45 e to the 3x minus 15 e to the 3x minus 30 e to the 3x. Okay, so that checks out. Now I'm going to save a little bit of time here, and I'm just going to kind of blow through a couple other properties. Number 2, does L of y1 plus y2 equal L of y1 plus L of y2? Right, now think about when we take derivatives of, say, x squared plus 5x. Well, what we really do when you take the derivative of x squared plus 5x, we just break that up into 2 derivatives. So it's pretty believable that this one works as well. So let's check that one. And finally, the third one I want to mention is does L of y1 times y2 equal L of y1 times L of, this is a times, y2. Okay, what do you think of that one? What if we had the derivative of x squared times 5x? We can't do that, can we? So this one does not work. And I put it in there because it's a common mistake, and we don't want to do that. So we have to use the product rule. Right, so don't do that. Okay, so back to our, so let's this is the end of the sidebar here. Back to our L, which was, let's see, d squared dx squared, nope, that was actually minus minus d dx minus 6. So the two solutions we came up with were e to the 3x and e to the negative 2x, right? I'm going to say that since L of e to the 3x, right, what did that equal? So when we apply this differential operator to e to the 3x, what does that equal? Well, that equals 0, right? That's what we were trying to figure out. And if L of e to the negative 2x, what did that equal? Well, that also equals 0. It made our original equation work. We can use one of these properties of differential operators to say that L of e to the 3x plus e to the negative 2x also equals 0. This is called linear superposition. Okay. Since this is equal to 0 and this is equal to 0, well, the sum of them must equal 0. And that leads us to a little theorem that we're going to stick in here. Where's my chapter 17? Linear superposition. Okay. Just barely fits. Perfect. So if P, Q, and R are continuous over the open interval I, and P of x is never 0 on I, then the linear homogeneous equation 2 has two linear, I didn't give you equation 2, has two linearly independent solutions. So we can just say this is equation 2 on y1 and y2, right? If it's a second order linear homogeneous equation, has two linearly independent solutions, y1 and y2. Moreover, if y1 and y2 are any two linearly independent solutions, like I could multiply by 13, I could multiply 1 by 7, the general solution is given by the total solution is y times c1, right? 13, 26, 19, whatever. Multiply it by whatever times e to the 3x plus any random constant times e to the negative 2x, right? The full solution, the general solution, includes one constant times my first solution plus my other constant times the other solution. So, in terms of linear operators, okay, L, our linear operator, operating on A times U plus B times V equals, I can factor out this constant A, L operating on U by itself, plus B times L operating on V by itself. Okay, that uses these two rules over here that we can treat a linear operator just like we treat a derivative. So let's move on here. Okay, what else do we have? For our example, since I'm going to write it down here, L of e to the 3x equals 0, and L of e to the negative 2x equals 0. The full solution is y equals c1 e to the 3x plus c2 e to the negative 2x. Remember back when I multiplied this 1 by 13 and it still worked? Well, that could be anything. It would always work. Likewise, this one would always work. So I've got two constants. Now, you may ask yourself, why do I need both of them? Why isn't one of them good enough? We could talk about that, but in general, that's something you learn in a differential equations class. So I'm gonna be a bit of a hypocrite here and say, trust me. If you want to challenge me, please ask me in class. But trust me for now. And as long as we're exercising some faith here, some rules that you should follow. For DiffEQs. Okay, so 1. If the characteristic equation, right, that stands for characteristic equation, gives two real roots. Okay, now two real roots such as 3 and negative 2, those are two real roots. Y equals c1 e to the r1x, right, the root 1, the first one. So you're wondering why I picked r way back when. Well, r because it stands for root. Plus c2 e to the r2x. All right, that's supposed to be a 2 there. Well, whatever. You'll figure it out. So number 2, if the characteristic equation gives a repeated root, repeated r, then you're going to write y equals, let's see, c1 e to the r1x plus c2 x e to the r1x, right? r1 is the only root here because it's repeated, you know, like x squared, if the characteristic equation was a perfect square, r squared plus 6x plus 9, something like that. You know, if we did it, if we didn't put this x in here, right, if we just said, well, you know, c1 e to the r1x plus c2, you know, in there, c2 e to the r1x, well, really, we would just have c1 plus c2, okay? So that wouldn't work out. 3, and this will be the topic of another video, if the characteristic equation gives two complex roots, right, such as r1 equals, let's call it alpha plus I beta, and then r2 equals, well, what would r2 be? If it's alpha plus I beta, the other root has to be, think about it, alpha minus I beta, right? From algebra class, way back when, the roots are complex conjugates. Now, what will my y be here? And this is crazy. This comes back to my favorite trig identities. It'll be e to the alpha x times c1 cosine beta x plus I sine beta x. Complex numbers. Oh man. Alright. I will explain that in another video. In fact, I'm gonna stop this video here because I know it's getting long, and in the next video we will work a couple examples. Okay. So we'll see you soon.